in Rio de Janeiro. And also she's studying physics, but she's also an expert on the history of physics, in particular 20th century developments in physical science. And today she will present us a presentation of work on quantization of black hole gravity.
Thank you. Thank you for this introduction. Yes, I am both a physicist and a historian of science, and trying to do both at the same time. So I'm going slowly at both research topics. But I'm here today to present my physics research, which is about the quantization of black hole gravity. Thank you again for this opportunity and to celebrate this special occasion that is the Professor Rachel-Doris Centennial. Let me try to share. I think I have to share the whole screen. And then I can do this. Can you see my presentation?
Yes.
Yes, okay. I cannot see you, so if you have any question, you can stop me at any moment, and I'll try to get back to the call to look at you.
Thanks, Carla.
Today, I'm going to talk about a paper that was published earlier this year. It's the quantization of a black hole gravity using geometrodynamics and the quantum phase formalism. I will explain what those are further. It was a work that I did with my co-author, Denis Rodriguez, which is his postdoctoral researcher at the PPG Cosmo at UFES, and our goal was to see if we could apply this quantization method, this new, it's not a new quantization method, but it's an alternative method of quantization to a black hole metric. So my talk will be divided into 6 parts. The first is why to quantize gravity, and I'll try to explain our motivation. I will explain the quantum formalism behind our paper, and then we'll talk about a little bit about the Hamiltonian of a black hole. We will quantize the black hole gravity and do a semi-classical analysis with, and then my closing arguments, that's my conclusion and future work. So first, why to quantize gravity? Our goal here is to investigate the vicinities of a singularity, right? Which is super fitting, considering I'm talking in celebration to Professor Rachel-Doris Centennial. He was very important to the history of general relativity singularity. So we were trying to investigate the vicinities of a black hole singularity. And the vicinity of a black hole singularity is an extreme region where both quantum effects and gravity are relevant, because as vicinity here, I'm talking really about the Planck radius around a singularity, let's say, in a Planck scale. And we know that the singularity is formed because of the drastic curvature in space-time. So both effects are relevant in this region that we are trying to study. Usually, these regions are studied with the ad hoc merge of quantum field theories and general relativity. We've seen it, for example, in, I'm sorry, I couldn't be here for all talk, but we've seen with Mark Casals talking about causality inside of a black hole. He did something like of this merge of quantum field theories and general relativity, or perturbations in quantum field theories, like the last speaker was talking about. But what we try to do here is to quantize gravity itself, not to do quantum field theory in curved space-time, not to try to do some special relativity quantum mechanics. It's to take the metric and quantize it. Quantize gravity itself. Let's put in this word. So an alternative is to quantize gravity itself and analyze the effects of the quantum corrections in the gravitational model. Okay. I have some disclaimers here. First, in the classical limit of, or if gravity can be disregarded, the quantized gravity model should recover general relativity or quantum mechanics. If, of course, you have no gravity, this quantization should recover the quantum mechanics, the usual quantum mechanics results. And if we are very far from the singularity, GR should be recovered, right? However, we will disregard for now the fundamental constants. H bar, C, and G will make it equal to 1. We did this first because we are trying to do an more qualitative analysis to see if our model has any future, but in the follow-up article that we are already working on, we will reinstate the fundamental constants to see, and I'll show you later what we can expect from this reinstatement. But for now, let's disregard this and just try to think about what kind of results can we get from this theory, this model. So our idea to quantize gravity is to through the Wheeler-DeWitt equation. So relativistic gravitational models are constrained systems, and the quantization of the Hamiltonian constraint, which is the Hamiltonian is 0, is called the Wheeler-DeWitt equation. It is given by the operator, Hamiltonian operator applied in the wave function of the systems is equal to 0. So we noticed a clear stark difference here from the usual quantum mechanics, right? We have what is called the problem of time. If we compare the Wheeler-DeWitt equation to the Schrödinger equation, we see that the left side here is missing a derivative of time, which means that the derivative of time of the wave function is 0, and then time basically disappears or is constant in the quantization of this theory. And this happens for a number of reasons. One, of course, is the different nature of time in the quantum theories and in the relativistic theories. In quantum mechanics, time is an universal parameter, like the universal time in Newtonian theories, while in general relativity, the time is a coordinate of space-time, so they cannot be separated from the spatial coordinates. Another reason why this problem arises comes from the 3+1 formalism of general relativity. If we're talking about the Hamiltonian formalism or the constraints of general relativity, we're talking about the Hamiltonian of general relativity. And to find the Hamiltonian, there is this formalism called 3+1 or ADM from Arnold, Deza, and Misner in the 60s. It was named after those three researchers, in which we foliate space-time into spatial hypersurfaces, and the norm of those hypersurfaces is given by time-like vector, right? And the metric of space-time in this 3+1 foliation is given by this ds square. This formula, this metric, I will not read it out loud. You can all see, I'm sure. And in this separation, in this rewriting of the space-time metric, the coefficients of the temporal coordinates are not dynamical. They are Lagrange multipliers of the constraints that we obtain from the theory, namely the Hamiltonian constraint that we talked about and the momentum constraint. So they are not dynamical functions. And if they do not have dynamics, the coefficients of time do not have dynamics, so time disappears in the Hamiltonian constraint, okay? In the Wheeler-DeWitt equation, sorry. Thus, the dynamic of the Wheeler-DeWitt equation should be imparted by an intrinsic parameter of the quantized systems. So here we have one that is the Wheeler-DeWitt equation, and we want it to look like a Schrodinger equation. So we need to find an internal parameter of the Hamiltonian that will have this this linearized term that will give the dynamics of the effective Hamiltonian. Let's put it like this. Spoiler, in our case, this intrinsic parameter is associated with the G00 coordinate of the Schwarzschild metric, so it comes from the geometry itself. But I'll get there in a moment. So I gave you a basic reason of how we are planning, why we plan to quantize gravity and how we are planning to do it. And the whole geometrodynamics comes from this, the constraint, the Hamiltonian constraint and the Wheeler-DeWitt equation. So I will talk briefly about the quantum formalism. I fully understand I'm skipping a lot of details, and there's a lot more to discuss here, but due to time constraints, I only have this 45 minutes, right? I cannot go into detail, but I hope I can at least spike enough curiosity of you to check out the full paper on the topic. So the quantum formalism we will use is not the canonical method. I brought here the canonical operators as we are used to see in quantum mechanics, and in quantum gravity as well, a lot of methods and models use the canonical operators as we do in quantum mechanics. That is, the position operator is equal to x times the function, and the momentum operator, it becomes the derivative of the space, right? Of the coordinate. And any other quantum operators that are a function of position and momentum are obtained by substituting the variables position q and momentum p for their respective canonical operators. So, for example, the Hamiltonian of general relativity, it is written in terms of a position and momentum, right? And with the canonical method, you will substitute the position for x and the momentum for a derivative of x. The classical function, however, q times p, requires a special treatment since the position operator and momentum operator do not commute. And for strictly positive variables, the kinetic energy, let's say the momentum square, is not self-adjoint. And if the kinetic energy is not self-adjoint, our Hamiltonian is not self-adjoint. And why is it important? Yes, it's important because in the quantum theories, the operators should be self-adjoint to have a real measurement. If they are not self-adjoint, they can have complex eigenvalues, right? Depending on the theory, with canonical operators, you can impose some boundary conditions, such as these strictly positive variables are the kinetic energy of those strictly positive variables are self-adjoint or have a self-adjoint extensions, but it's something imposed by hand. Okay. So our goal is to change, not use the canonical method, but another quantization method, which is the integral covariant quantization method. I'm not sure if I wrote that right. I think it's covariant integral quantization method. It's maybe it's I had to change this, but to change integral and covariant. I will not here give a deep explanation why this method is better suited for our case than the canonical method, but just mention some general features because it is quite complex. It has a lot of mathematical background. You see this kind of mathematical methods of quantization since von Neumann in the 60s as well. And there's a lot of reasoning why one should change the canonical method to another method. And this one is really nice because it is based on the symmetry of the phase space. That is, it depends on its algebra. So you get to keep all of the symmetries that's going on the phase space. That is the plane. I'm calling the phase space, but it's the cotangent space, right? It's the momentum, position versus momentum space. for all purpose, it's a phase space. So we get to keep all the symmetries of the phase space, which is nice. We want to quantize strictly positive variables, and I just mentioned that the canonical canonical method has some issues with this, and we can avoid those issues using this method. For this case, the symmetry group acting on the phase space is the affine group, so we will call this the affine quantization method, but it's the same. If I mention covariant integral, and affine is the same. Affine is just specifying that we are dealing with strictly positive variables. And what kind of variables we deal that are strictly positive? For example, in cosmology, we have the scale factor that gives the volume of the universe, right? It starts 0 and goes to infinity. So that's one example. In our case, I will show you later which is the variable and its interpretation. I'm sorry about the noise. Also, we want to quantize any classical function or distribution. For example, if you want to quantize a distribution like, for example, the Dirac function, with the canonical method, we cannot do it. But with the integral covariant quantization, we can do it. And any other classical function, we can quantize via this method. So let's combine the affine quantization and the integral method to build our quantum operators. So this is just an overview of how we build the operators. We need to use a fiducial vector or wavelets. They appear in the final version of the operator as constants. So the fiducial vector that we choose, they will calibrate the operator, okay? And we'll build the operator as such. For any given function or distribution f of position and momentum, its quantum operator, AF, is given by this formula. So this is a nice formula. You have this C gamma here are constants given by this defined as the integral of the wavelets, the square of the wavelets. Okay. So this is how the wavelets will impact the quantum operator. They will appear as constants. Later, another spoiler, we will need two operators for our quantized version, which will be the position operator to the factor beta is given by the position operator to power of beta and a constant in front of Q that we can calibrate with the right choice of the fiducial vector. For the operator Q square, P square, we will have this more complex operator given by, I should have removed it since I set it to 1, but it's a C0, C minus 2, a constant. We will have position square, derivative square, plus 3 position derivative times the derivative plus a constant here. These are the two quantum operators that we will need in the future, but they are calculated by using this formula for AF. Okay, and we get this nice round operator that we can apply. So let's talk about the Hamiltonian of black hole. Finally, we'll get to the black hole part. I gave reason to quantize gravity and how we would do it. I told you what is the formalism I'm using for the quantum method. Now let's talk about black hole. Considering the metric, the Schwarzschild metric, right? According to the Birkhoff theorem, any spherically symmetric solution for the Einstein equation is the Schwarzschild metric, or Heisner-Nordström if charged. So we have ds square written in this format, where A is equal to n, the inverted of n, 1 over n, and the Hamiltonian of the system described by this metric can be found applying the 3+1 formula for general relativity. We got it. We did not do this. This is quite famous paper that finds the Hamiltonian of this kind of solution. Writing with this, with this canonical transformation, alpha equals to ln natural logarithm of A, and beta equals to square of A times B. B here is it's basically the radius, right? The R square multiplying the solid angle. So it's B is basically the radius. And we'll also use this other canonical transformation, which T equals alpha over the momentum of alpha, and therefore PT, the momentum of T, is given by P alpha square over 2. We can find the Hamiltonian of the black hole, the Schwarzschild black hole, right? As given in these coordinates, is given by this formula H. It's quite nice, very, very simple. Here we have sigma is the sign of A, and I'll tell you what this means, but I avoided a lot of boring calculations, and you have to trust me this one for now, but you can also look at the reference later, that we get this Hamiltonian for this metric, okay, written in these canonical variables. For a Schwarzschild black hole, sigma equals 1 means the region on the exterior of the black hole, since the metric has signature minus plus plus plus. Let me get back here on the ds square. If we have sigma equals 1, sigma is the sign of A, then A is positive. If A is positive, we have signature minus plus plus plus. Okay, and if the sigma is equal minus 1, it represents the region on the interior of a black hole. That is, the coefficients for time and radius, they change signs, and the signature becomes plus minus plus plus. Okay, I think this is quite clear. If not, let me know. And the coordinate beta spans from 0 to infinity. Let me show you here. We have the module of A, so A is positive. So this is positive, and B is the radius that I told you. So the lower value of beta is 0, and it goes to infinity. Okay. Let me see. And the only way to differentiate the interior from the exterior of the black hole is through sigma. The Hamiltonian constraint that we see, which is H equals 0, if we take this formula and make it equals to 0, we get this nice equation. Beta square, p beta square minus 8pt minus sigma b square equals to 0. So here we start to see, maybe you are getting a hint of where I'm going with this. Let me see, I have to accelerate a little bit. If we had used the coordinates alpha and beta instead of t and beta, the quantization of the Hamiltonian constraint would lead to a Wheeler-DeWitt equation that, in principle, can be analytically solved. However, the lack of a dominant linear term in the differential equation could lead to a double arrow of time. Here, you see that the momentum of the variable t appears linearly in the equation. And this variable t is what will give the dynamics of the Hamiltonian. Okay, if it was squared, we would have a double arrow of time. There are papers that deal with a double arrow of time, but we wanted to avoid it, so we did the canonical transformation. And just to show you, the canonical transformation is T is alpha over PA, and alpha is directly connected to A. That is to the coefficient of the time in the geometry. Okay. We can correlate beta to the volume of the Einstein-Rosen bridge connecting two black holes in a thermofeed dynamics. So for late times, the volume of an Einstein-Rosen bridge is given by this formula, which is for small b, for small radius, approaches b minus 1. So for a small radius, the volume of the Einstein-Rosen bridge is equivalent to beta to the 4th. Okay, so we have these two coordinates. One will give the intrinsic entropic time, we call it entropic time, and the other has this physical interpretation of the volume of an Einstein-Rosen bridge. So the Hamiltonian constraint is this one, and the coordinate beta is related to the volume of the Einstein-Rosen bridge, and T is identified as the entropic time. We noticed that volume equals to 0, no bridge is formed, and we have a classical black hole with a singularity at its origin. Okay, so we are considering a possibility of getting a wormhole solution out of a black hole solution. So to take a better look at the T parameter, the time parameter of our intrinsic entropic time, we can analyze for the interior of the event horizon, which is the region we are trying to analyze, right? So the interior is sigma equals to -1. The region inside of the event horizon, we get a change, a sign change between the GTT and GRR, and the coordinate transformation T, changing T to R and R to T results in the homogeneous and anisotropic Kantowski-Sars cosmological solution, which is basically the Schwarzschild solution in the interior of black hole. Why we are using the Kantowski-Sars? Because we are concerned with the interior of black hole. So let's see what the time has, how the time connects to the cosmic time parameter T. In this metric, time is equals to this function of T. Okay. Let me show you with a graphic representation. So for the cosmic time, we have, it depends, of course, it depends on M. M is the mass of the black hole. The mass contained into the singularities. So for M, different M's, we see how this entropic time T, larger T, connects to the cosmic time, which is the little t. First of all, we see that while the cosmic time starts at 0 and goes to infinity, our entropic time, it goes from minus infinity to a certain point. So it is not strictly positive. It goes from minus infinity to a positive value. We see here that it approaches an asymptote and approaches a constant value. And that is to be expected. Remember that I told you that away from the singularity, there is for larger times, for later in time, the general relativity should prevail instead of quantum mechanics. And if general relativity prevails, the Hamiltonian constraint should hold. So the derivative of the wave function in time should go to 0. And we see this because time gets constant. So if time is constant for later cosmic times, the derivative of the wave function will lead to a 0, and then we recover the Hamiltonian constraint. These peaks here, these undulations, they are interesting. We see that the more massive the black hole, the entropic time it approaches, this peak slows down. So supermassive black holes, they would do almost monotonic relation between cosmic time and entropic time. Yeah, I think that's it. Okay. So enough about the time. Let's talk about the quantization of the black hole gravity. The quantization of the Hamiltonian constraint leads to the Wheeler-DeWitt equation. So it's just a Hamiltonian constraint, and now we instead of the variables, we have the quantum operators related to those variables, and the wave function equals to 0. For the coordinate beta, we will apply the affine quantization method that I mentioned before. The coordinate t has the whole line as its domain, as I just mentioned. And thus the symmetry group acting on the phase space is the Weyl-Heisenberg group. So we would apply the Weyl-Heisenberg quantization method. And the Weyl-Heisenberg quantization method is equivalent to the canonical quantization. So this is nice. We can, even with this covariant integral quantization, we can recover the canonical quantization for the right variable, right? For the space-time, for a phase space that is the whole plane. So this operator I showed you before, they appear in this, in the right side of the Schrödinger-like equation, and the operator for the momentum of t, we use the canonical quantization, and we get minus derivative of t of the wave function. And this, now we get a Schrödinger-like equation, and we do our usual quantum analysis from this. The general solution for this equation is this one. So we have a nice, clean wave function of the universe, of the black hole in this case. We have a wave function for the black hole. These are Bessel functions. N1 and N2 are constants. E is the energy of the system. Eta is given by this constant. Okay? And we have sigma here. So before analyzing the boundary conditions to determine N1 and N2 and E, we should specify sigma. We are, of course, interested in the interior of a black hole, so sigma should be -1. And in this case, N2 equals to 0, and eta is, this is not an eta, it's a nu, right? It's a nu. And nu is natural, goes from 0 to 1, to infinity. Natural plus 0. So otherwise, the solution is not well defined at the origin. The origin here is beta equals to 0. So we call nu equals n because it's a natural number, and we obtain a discrete energy spectrum for the system. So this quantized black hole has a discrete energy spectrum. And the wave function that describes the black hole is given now by this, the sum of the states, okay? Each state is given by beta -1, a Bessel function of beta, E, exponential of E, energy times time. Okay? As usual, we can normalize the wave function, and we have a nice normalized wave function by given in this formal, this last equation right here. So cool, we have a nice wave function of the universe, of the black hole, sorry. we have energy levels for the black hole, which is super cool. Discrete energy levels. And we can draw some conclusions. Let me come back here. Notice that the energy levels, it is a constant, right? But they depend on the fiducial vector. So these C's here, they depend on the choice of the fiducial vector during the quantization. Remember I told you? So they depend on the fiducial vector. The wave function does not depend on the choice of fiducial vector. The wave function is free from the choice. So yes, to specify an energy level, we have to specify a fiducial vector. But we can infer we can get some results even without specifying the fiducial vector. For example, the ground energy level is always negative. A negative energy could indicate that at least the ground state of the black hole might be a wormhole solution by direct violation of the null energy condition. Okay, so we get to see that at least for lower energy levels, we might have a wormhole solution instead of a black hole solution. And now we can do a semi-classical analysis. We have this is the result that we wanted for the quantized black hole. We have discrete energy levels, we have a wave function, we have that the lower energy levels might be wormhole solutions, and now we can go to a semi-classical analysis and see what it does tell us. The covariant integral quantization, now I wrote it right, the covariant integral instead of integral covariant. The covariant integral quantization method has a straightforward quantization map. So you can get a classical function and make it into a quantum operator, AF, and we can also dequantize this operator to find another classical function that in principle is different, is, let's say, quantum corrected. So this F check is the quantum correction, is the classical function that is the quantum correction of the initial function, okay? And it is defined this way. This quantization method is you get the quantum operator and you get the expected. It's not the expected value because it's not on the X space, but in the phase space. Okay, so it's Q and P instead of X. But yeah, this is the quantization map. And it is given by this huge formula, but we can calculate it. It's doable, it's feasible, and it's a lot of work, but we can do it. Classically, we have the identification of the Hamiltonian as the total energy of the system, right? So we have the check of the Hamiltonian as the energy levels. But if we do the check version of the Hamiltonian constraint, we find this nice, sweet simple equation. And E here is the momentum of T. It is the quantum correction of the momentum of T. Okay, so we have also a correction for the classical Hamiltonian. So equation 2 becomes then a quantum correction for the Hamiltonian constraint. And we can get valuable insight from this phase-space portrait that we call it in a qualitative analysis of the model. For example, if beta becomes null at some point, classically, the black hole has a singularity in its interior. If, however, the volume is never zero, the geometry suggests the formation of an Einstein-Rosen bridge of the wormhole. For the sake of providing an example, I chose a fiducial vector, which is quite nice, and this equation 2 becomes this last equation here. This is for the interior of the black hole, right? We are always talking about the interior here. So for higher energy levels, for greater energy levels, it should be higher. Yeah. The volume contraction speeds near the origin here, which remains in asymptote. So beta does go to zero, right? Beta can contract until zero here. It comes, the momentum gives the velocity, right? So it comes really, really slow, and when it gets closer to zero, it speeds up to the singularity. So yes, for higher energy levels, we still get a black hole with a singularity inside. However, for lower energy levels, and we have, remember, for lower energy levels, we get negative energy, right? And with this negative energy, we see that there is an asymptote before the zero. We have a minimum volume. This lambda is beta, actually, this p beta and beta. So we have a minimum volume. And we notice the formation of an Einstein-Rosen bridge. So our conclusions, just to close it up, I think I'm on time, yes. We use the covariant integral quantization method, which we argued is more suitable for variables in different domains. We established that the evolution of the quantized system is given by an intrinsic variable that imparts dynamic to the model. This entropic time plays the role of a Newtonian clock, a universal time parameter. After identifying the time parameter, we recovered a Schrödinger-like equation obtaining an effective Hamiltonian operator that governs the model. And the solution of this Schrödinger-like equation is a combination of polynomials, Bessel functions, and the time exponential. The system's energy spectrum is discrete in the black hole's interior, and the ground state has negative energy, which suggests it could be a wormhole solution. The semi-classical analysis supports this last conclusion. So we got this at the quantized version and the semi-classical analysis. So which are the next steps? First, we have to reinstate the fundamental constants, G, C, and H, to investigate the thermodynamical implications of its quantization, and to probe how sensitive the energy is to the choice of fiducial vectors. So here we are trying, this is a work I'm doing with Denise, which is my co-author, but also with the help of Alexandre Almeida and Emmanuel Frion. We are trying to reinstate the fundamental constants to see, for example, what is the interpretation of those energy levels? Because I'm talking about energy of a black hole, but I didn't actually say what the energy of a black hole is. If our interpretation is correct, we assume this is the difference in energy is the Hawking radiation. So for example, to the jump from one energy level to another causes the black hole to radiate, or if it's eating matter, it eats matter and jumps for a greater level. But if it's evaporating, it will go energy state by energy state, and in these energy jumps, it will radiate the same amount as the Hawking radiation. This is what we expect, and what we are trying to see if it occurs. We will analyze the cases of micro black holes. You see that we did all of this analysis to the interior of black holes, but if we use the exterior of a black hole, we can analyze the vicinities of the event horizon, right? So we can do this whole calculation again to the exterior of the black hole and see what we can find. Because, quantum gravity will become relevant near the event horizon as well. And another goal would be to extend these results to the case of charged black holes and rotating black holes, which is, this one is more, quite ambitious, I think, because there will be a lot of more complications I foresee. So this is it. Thank you very much. This is the paper that that I based this presentation on. We have way more details in the paper that I could not share here, but yes, so it's published at Classifying Quantum Gravity. Thank you.
Thank you, Carla, for the really interesting talk. Is there any question?
Oh yes, just in time, yes. What does the peak correspond? I'm thinking you're talking about the graphic. Let me, I will get back to the. This, right? It doesn't, it says that the dynamics inside the black hole is not as straightforward as we imagine compared to the cosmic time. Because we think in terms of cosmic time, right? So if we think in terms of cosmic time, this means that the intrinsic time can flow backwards. But this is not the correct interpretation, because the cosmic time is not how we imagine it to be inside of a black hole. So This peak here just tells me that the dynamic, the kinematics inside of a black hole is not as straightforward as we imagine it to be. I think this is the answer. You are not my brother. Okay.
Any other question? So actually, I have a doubt, Carla. When you were showing us the discrete energy spectrum, once you were able to quantize the black hole interior and so on, you mentioned, now I cannot recall precisely, maybe if you can get back to the slide, corresponding slide. Because if I remember correctly, there was a limit that you mentioned for approaching for beta that was going to 0.
Yes. So this is not about the energy. The energy is a constant. Each level is a constant. So this is the energy we got. C0 is a constant, C minus 2 is a constant, C minus 2, 1 is a constant. This whole energy is a constant, okay?
I see.
What we did was to analyze the correct semi-classical Hamiltonian. So the semi-classical Hamiltonian here, it depends on the energy, right?
Yes.
So for different energy levels, we have a different semi-classical function. So E1 will give us one curve. E2 will give us another curve. So here we have energy level 4. We have this solid line here, which the graphic is not so good. It seems it stops at 0, but it's actually go asymptotic 0.
I see.
But so for the 4th energy level, we have this curve. For the 5th, we have this curve. So all curves, they look alike, just change the energy a bit. Okay? So more energy means that the black hole, the radius of the black hole is accelerates quicker. Okay.
Okay. I see.
And for lower energy levels, so we have ground state, energy level 1, energy level 2, and energy level 3. For this choice of Dushel vector, we have something like this: a minimal volume, and it gets constant. So we have very clear from that we do not reach 0. Okay, so the beta does not reach 0, and beta is the volume of the wormhole, basically.
Yes.
So if beta does not reach 0, it does not have a singularity, and we have a wormhole instead.
Okay, but these two scenarios are not like consequential in time. They're all like
They can be. Yes, this is what we want to. This is what we want to analyze. If our interpretation is correct, we get to see. You get to think on a black hole evaporating. So we have an evaporating black hole. We have a higher energy level. It evaporates to a lower energy level, and then evaporates more to a lower level. And we have a black hole, it evaporates to a black hole, evaporates into a black hole. At one point, so the black hole disappears and the wormhole is formed. And this could mean that the final is, that's what happened to the information inside of a black hole. It is used to create this wormhole. Wormholes are notoriously unstable, so it disappears at one point. So it could be sequential in time, but to prove this point, we are working towards a thermodynamic analysis, reinstating the constants, and this is what we are hoping to get with this next paper. Yes.
I see. And in that case, like if your assumption might prove correct, the formation and later on disappearance of a wormhole might like avoid like the creation of a naked singularity, or otherwise like
it might, yes, it surely avoids, surely avoids, yes.
Really interesting.
Yes.
Thanks, Carla.
I hope that the equations agree with my suspicions, but we have to do the calculations first.
Yes.
But this
Let's
is
hope so.
what we are trying to do. This first paper was to investigate if it was possible to make an analysis out of this quantized model, and we see that it's possible. Now we will investigate further on this.
Perfect. Thanks. If there are no other questions, okay, so thanks once again, Carla, for accepting the invitation and presenting her work during this event. And so we have finally, unfortunately, reached the end of this event. I would like to once more thank all the speakers and who have participated in this event, all the PhD students,